So hi everyone, so this is a new chapter. This is chapter 2 on capacitor and dielectrics. So let's write it down. Capacitors and dielectrics. Okay, so in this particular section, this is section 1. We are going to talk about capacitors and capacitance. Okay, so let me write it down clearly. This is C2S1 that we are going to discuss right now. Chapter 2, section 1. And chapter 2, section 1 is on capacitors. We'll learn about capacitors. And we'll learn about a physical quantity that is called capacitance. Okay, two things. One is what is capacitor first. Then afterwards, we'll learn about capacitance. So these are the two important things that we will learn for section 1. Okay, so for now, the main idea of a capacitor. Okay, let me write a capacitor. Maybe not this color. Okay, a simple way of talking about what is capacitor. A capacitor is just a device that store electrical energy in the form of electric charge. Okay, you can say it's a device that store electric charge. And because it stores electric charge, therefore the device itself will store electric energy. Okay, where is the energy being stored? Later we'll discuss in greater detail. But for now, just know that it's a device that can store charge. And because it stores charge, it will store energy. Okay, so right now, I will straight away jump into a small section, small topic, in which I'm going to talk about how does a capacitor work. Okay, so a capacitor look something like this. Okay, so this is a capacitor. You can see that it has a bulb here, then it has not bulb, it has a unit over here, then it has two legs over here. So one leg will be positive leg, one leg will be negative leg. There are certain capacitors that don't have positive negative polarity. There are certain capacitors that has polarity. In this case, this one here has polarity. Okay, so in terms of a circuit diagram, if you draw a capacitor in a circuit diagram, the symbol for a capacitor, we are going to draw it as something like this. This is how a capacitor would look like. Okay, this is the wire. Then we draw it as a pair of parallel plate. Okay, so this is how we draw a capacitor. So I say it's a device that stores charge, but how does it store charge? Is what I'm going to discuss in this subsection over here. How do we store charge and how do we lose the charge? How do we store the energy? How do we lose the energy is what I'm going to discuss now. So I'm going to talk to you about the concept of charging. Charging means by you are storing electric charge. The first concept is the concept of charging. And the second concept that I'm going to discuss with you is the concept of discharging. So we have to roughly understand how does a capacitor work first. A capacitor works by charging charge in it, storing charge in it, and releasing charge. So the process of storing the charge in it is called charging. The process of releasing the charge that has been stored earlier is called discharging. So how do we make a charging process happen? Well, you can connect your capacitor. Okay, this is your capacitor. Okay, I'm going to redraw the diagram that I drew just now. So this is a capacitor. If you want to charge a capacitor, what you need to do is you need to connect the capacitor to something like a power supply, something that supplies energy. In this case, we know that the simplest electrical device, electrical component that supplies energy is a battery, right? So we are going to connect it to a battery. Okay, usually you cannot just connect it directly to a battery. You need something like a resistor. Okay, but that is not our focus here. Our focus here is to understand how does this how does this capacitor store charge? This is our focus. Okay, so to understand the idea, let me start with a situation where you have a capacitor which has no charge being stored at all. Okay, so I'm going to say this capacitor that you see right now is uncharged. Okay, and now I make the two plates over here to become a physical rectangle that you can see. So this is representing the two plates that you see over here. And as you can see in the diagram here, I'm connecting it to a battery and a resistor. But again, resistor is not my focus for this particular section. Later on in section 3, I will talk about it. But for now, it is not the focus. So I'm going to just draw it to be connected to the battery for now. Okay. So this capacitor here is going, okay, not yet, going to be connected to a battery. Okay, so I'm drawing the battery over here. Because I say it's going to, I'm going to leave the switch open, because in the future when I close the switch, that's where the charging process will start. Okay, so right now it's uncharged because I still haven't started the process of charging. So there's no charge being stored at all in the capacitor. So how does the inside looks like of a capacitor when it is uncharged? Uncharged means that you are storing no charge is being stored. So if you imagine it, it'll be something like this, okay? You have some amount of positive charge in both plates, but that amount of positive charge must be balanced also by negative charge. So if you have, let's say, 4 positive charge on top, you'll be balanced by 4 negative charge on top. If you have 4 positive charge below, you'll be balanced by 4 negative charge below. So if you look solely at one single plate, you see the number of positive charge and the number of negative charge, they are the same. So if they are the same, you can call it as electrically neutral. So the upper plate is neutral and the lower plate is neutral. So right now it is uncharged. Okay, there's no amount of charge being stored in it at all. Okay, but now what happened is you're going to close the switch. You're going to close the switch. So as you close the switch, what happened is the charging process will occur. So from here to here, you should imagine that the charging is happening. Okay, so it's still the same setup. We are still connected to the battery. So I'm going to draw the battery once again. But right now the switch is already closed, so I'm not going to draw it going upwards. The switch is already closed. So it looks something like this. Okay, so what happened is when you connect this capacitor, okay, the two legs of the capacitor, when you connect it to a battery, what happened is the battery serves as a pump. Charge pump, okay, maybe a charge pump, maybe that makes sense. Okay, so a normal pump or a water pump, you pump water. So pump water, usually you use a water pump to pump water from a lower place, you pump it up to the second floor of your house to a higher place. So in this case, the idea of how a pump works is, okay, for battery, what happens is it's going to move positive charges. Okay, the idea is it's going to move positive charges from the negative terminal to the positive terminal. I hope all of you are clear that this is a negative terminal, the shorter leg, whereas the longer leg here represents the positive terminal. So a battery always push positive charges from a negative terminal to the positive terminal. So this is how your charge will move across the battery. You will be pumping charges across the battery in this direction. So if you're pumping charges in this direction, what happened is okay, you will have loss of charges, positive charges from the lower plate. Okay, your negative charges remain unchanged, so I'm talking about the positive charges. I'm not talking about the negative charges at all. So negative charges remains the same, but what happened is there are positive charges being pumped out of the lower plate, so it's being drawn out of the lower plate. The positive charges are being drawn out from the lower plate and is being pumped by this battery here, or we call it as a charge pump. Then it will be pushed into the upper plate over here. So the upper plate will experience a gain of positive charges, whereas the lower plate here will experience a loss of positive charges. So for example, I'm going to leave only one single negative charge here, positive charge here, sorry. So maybe one of the positive charge is still on the way, another positive charge is still on the way, another positive charge has already arrived. So initially there was already three, how did I draw it? Initially there's already four right up here. Initially, if you look over here, there's already four positive charges over here. There's already four positive charges over here. But right now you can see that the lower plate, there's some positive charge being drawn out. So there's one positive charge being drawn out, second positive charge being drawn out, third positive charge being drawn out, and maybe the third positive charge has already reached the positive plate. So you can see you can already reach the upper plate. So right now you can see that upper plate over here has 5 positive charges and 4 negative charges. Okay, so you can see that there's more positive charges than negative charges. Therefore, the upper plate become net positive right now. The upper plate is right now net positive charge. So there's a positive charge stored in the upper plate. If you look at the lower plate right now, the lower plate has a certain amount of negative charge, and the number of negative charge is less. The number of negative charge is more than the positive charge. There's more negative charge than the positive charge. Therefore, this plate right now will be negatively charged. Okay, so this process will goes on. The charge will move along this direction. The positive charge move along this direction. So at some point, the positive charge will accumulate more and more and more and more and more. So if you accumulate more and more and more, at a certain point, you will see that there's a maximum amount of charge that can be stored has already been pushed up there. Okay, so you can probably think there's something like this in the plate. There's already the 4 existing positive charges, but another 4 has already been brought up. The number of negative charge remain the same up here. Okay. On the other hand, on the lower plate, you see that all the positive charges being drawn out. Okay, I'm just showing it pictorially. It's not exactly true that all the positive charges will be removed from the lower plate. Okay, it's just a certain portion will be moved from the lower plate to the upper plate. And up here, they receive some amount of positive charge, but not all the charges will move to the upper plate. I'm just showing you the illustration of how everything works. Okay, so of course this process happens only because there's a battery being connected to it, so please don't forget our battery in our discussion. Right. Okay, so right now you can see there's a maximum number of positive charges being accumulated over here. Then the negative plate here already lost the maximum amount of positive charge that it can lose. Okay, of course in a real life situation there's millions to billions of this kind of charges. I'm just talking like a simplified diagram to illustrate the situation. Okay, so when you reach a point that you cannot shift any more positive charges to the upper plate, you just shift a maximum amount of positive charges to the upper plate, there's no more charges that can be moved, then you can say that the situation here, the capacitor has already been fully charged. So the capacitor right now is fully charged. Okay, so when it's fully charged, in section 3 later, we'll learn that if it's fully charged, we usually represent it by positive Q naught and negative Q naught. Okay, so the amount of charge being stored in this capacitor right now has reached its maximum. So we can say the capacitor is fully charged. Okay, so right now, if you recall a bit of what you have learned from chapter 1, chapter 1 already tell you that if you have a pair of parallel plates and it's oppositely charged, where you have one plate is positive and one plate is negative, what happens in between the two plates is there will be a uniform electric field being formed, right? So using our idea that we learned from chapter 1, we should know that when the positive charges arrives at this plate, and when there's some amount of positive charge being accumulated here, and some loss of positive charge resulted in accumulation of negative charge over here, when this situation happen, there will be potential difference across the two plates. This one will be V high, this one will be V low. So we should probably record that. This one will be V high. This one will be V low. And because there's a potential difference, you learn that delta V over D, right? When there's a potential difference and the distance, you have electric field in it. So what happened is there will be electric field formed in between the two plates. So right now there will be electric field formed between the two plates. So maybe initially, because there's only a little bit of charges being accumulated, you see that your electric field is very mild at this moment. But later, when it's fully charged, you can see that the potential difference between the two plates become very big. This is super V high, very high V. This is V low, super V low, okay, very low V. This one will be the maximum V. This one will be reach the V low, the lowest possible V. At that moment, it usually reaches maximum. So you can see that there's a strong electric field being formed in between the plates. Okay, the electric field gets stronger. So you see something like this. Okay, the initial two lines also still exist, but right now there's more than just that. Okay, the electric field grows to become stronger. Okay, so this is the situation in which we are charging our capacitor, where we are bringing charges from one of the plate, or positive charges from one of the plate, we shift it to another plate with the aid of a battery. This battery is helping this process of moving the charge, positive charge, from one of the plate to the another plate. Okay, how do you know which charge move from upper plate to lower plate or lower plate to upper plate? Look at the direction of the battery. Battery always push positive charges from negative to positive terminal. So you know if your charge is moving, positive charge is moving this direction, you know that the positive charge will have to be drained out from the or draw out from the lower plate, and the positive charge will enter the higher plate. This will allows you to know where is the direction in which the charges will flow. Okay, so this is the process of charging. Now let's talk about the process of discharging. Okay, we store the energy now inside this capacitor. Okay, the energy is actually stored inside this electric field, but it is only useful if we can release the energy to do something useful. Okay, if you release the energy being stored inside here in a charged capacitor, if you are able to release it to a light bulb and make the light bulb lights up, then it makes the capacitor a practical thing that can be used in real life. You don't want a device that can only charge but cannot discharge. You want it to be able to release the energy to do something useful. So to release an energy to do something useful, we have to look at this part over here where we learn about discharging. Okay, so right now, what happened is you still have your capacitor, but you want to discharge the capacitor. So if you want to discharge the capacitor, that means by your capacitor have to be initially already charged. Okay, you already went through a charging process. So right now it is charged already. Okay, so right now this one is fully charged, waiting to release the energy. The energy is stored inside there, waiting to be released. So how do you release the energy? It's actually very simple. Okay, what you need to do is just to connect this capacitor with maybe, let's say, like a light bulb. Okay, if you want to connect it, you want to supply the energy to a light bulb, then you apply that, connect it to a light bulb. Okay, so when you connect it to a light bulb, what happened is what happened is the battery is no longer there. Okay, this setup over here, there's no more battery inside this setup. So if there's no battery inside this setup, there's no more pump over here to force the positive charge from this lower plate to the upper plate. The driving force is no longer there. No one is pushing it up to the upper plate anymore. Okay, but if you just leave it blank, let's say if you just leave it blank like this, what happened is nothing will happen. Nothing will happen means by the positive charge that was already accumulated just now will still remain on the upper plate. The negative charge that was initially not moving, let's say in this case not moving, will remain like this. Okay, the situation will remain like this if you remove the battery. Why it will remain like this if you remove the battery is because there is no path for the charge to flow back to the lower plate. They are very eagerly want to go back down to the lower plate. But as you can see here, if I remove the battery, the circuit is not fully connected. There's a missing gap. There's a gap over here. So the charge cannot really flow down to the lower plate. Okay, so in this case, we can say the capacitor is stored with charge and the energy is stored in the capacitor, but you can bring it anywhere as long as you don't connect the two legs. So right now it's a charged capacitor where you can connect it to a light bulb, then it lights up. If you connect it to an beeper, then you beep. Okay, but if you don't connect it to anything, the charge remain inside being stored. Okay, so right now if I connect it to let's say a light bulb, what happened is right now the circuit has been connected. There's a complete path for the charge to move from the upper plate, which has a lot of positive charge, and you move down to the lower plate here, which has negative charge. Okay, you can see there's a lot of positive charge over here, so they will repel each other very strongly, so they will squeeze the positive charge out from here. So you will see positive charge leaving the upper plate, and they are now gushing down to the lower plate. Okay, there's no more pump forcing it at the upper plate. So right now what will happen is they will want to return back to the lower plate. So you see some positive charges moving. There's some accumulated over here already, reach here already. Okay, so this process of discharging will happen only when you start to connect it to a certain load. Okay, I'm not supposed to draw this right now. I think I messed up my drawing. Let me edit a little. Okay, I want to draw the first diagram to be nothing happen at all. Okay, so I'm going to leave the switch open. It's not connected yet. But right now we know that it's fully charged. It's not connected, but it's fully charged. Okay, so the moment I close this switch, that's where the discharging start to happen. The release of charge start to happen. The release of energy starts to happen. Okay, it has been connected right now. So as I mentioned just now, initially there was a lot of positive charge up here. But what happened is the positive charge, they all repel very strongly. Positive like charges repel, right? So they push the positive charge out of this plate. So you can see positive charge will be gushing down to the lower plate. Because lower plate, there's only negative charge, right? So it'll be attracted to it, you gush down to the lower plate. So you see some positive charges leaving the upper plate, and you see them rushing down to the lower plate. Okay, so we can say that right now there's a release of energy because the charge that is being stored is being reduced. Initially, there's a lot of charge being stored, but right now the charge are going back to the lower plate, so the amount of charge being stored right now will reduce. Okay, if initially it is fully charged, initially if it's positive Q0, Q naught, positive Q naught, initially if it's fully charged, right now it is no longer fully charged, it's just partially charged. Okay, it's like your phone battery. Just now it was 100%, right now it's 70%, something like that. So it becomes less fully charged. Okay, so you can say this is the process of discharging. Okay, initially it was fully charged, but right now it undergoes a process of discharging, where charge are moving out from their plate, moving back to the low potential plate. Okay, so positive charge will be exiting this plate, going back down to this plate over here. So when all the positive charges that was accumulated gets back down to the normal to the lower plate, then there's no more charge being stored, right? So when there's no more charge being stored, at the end of the discharging journey, you see your capacitor right now go back to being uncharged. Okay, so when it goes back to being uncharged, what happened is all the positive charge that was initially accumulated will now go back down to its original plate already. Okay, so things get back to how it was before it was charged. So this was the initial situation. So it has lost all of its charges. It has lost all of its energy. If you insist on writing it, the amount of charge stored is now 0. Okay, so this is how the discharging process works. And of course, if the charge pass through the light bulb, that's where the charge will give energy to the light bulb to light up the light bulb. Okay, but the energy part we'll discuss about it later. For now, just know that the charge will pass through the positive charge will pass through the light bulb, and as it passes through the light bulb lights up. Why does it work that way? Later we'll discuss about it. Okay, now we talk about the electric potential and also the electric field. So if it's fully charged, there's a very high potential over here. There's a very low potential over here. So initially the electric field in between these two plates will be a very strong electric field. Okay, yeah. Okay, but as you discharge the capacitor, then there's less charge inside the capacitor, right? So there's less charge inside the capacitor. The V high is not so high anymore. The V low is also not so big anymore. So right now the electric field will be a smaller electric field. And at the end, there's no electric potential at all. The electric potential between them, it will be 0, so there's no electric field anymore. Okay, so this is a situation in which we are going to discuss where you talk about capacitor being charged or discharged. Okay, so I want you to take notice of the movement of the charge. When it's charging, right, you see that the charge move in a certain direction. But when it comes to discharging, you see that the charge move in the opposite direction. Previously, there was this battery here trying to pump the charges from one plate to another plate. But right now, when you remove the battery, what happens is, if you connect it to another load, there's no more battery forcing the charge to this direction. So the charge will flow back down to its original plate. That's why when it flows past through the component, it will cause the component to be functional, either light up or produce a sound, something like that. So this is how we use the capacitor in the most basic way. There's many ways to use a capacitor, but this is how we use it in the most basic way. Okay. Actually, there's an important thing I want to discuss. Okay, I'm not sure whether it'll be relevant for you to understand, but usually when I talk about capacitor, right, I relate it to like a water wheel. Okay, so this is a water wheel. As you can see, this is the wheel, and you have water flowing from higher ground to lower ground. Okay, so this is my notes. You can access it from my website. Okay, so we know that if we have water flowing from higher ground to lower ground, what happens is the water will loses gravitational potential energy. Initially, the water is at the high place, so the H is big, so mgh will be big. So the gravitational potential energy of the water when it's at higher ground will be a higher value. But when it goes down, when it flows downward, what happens is the H decreases, right? So the potential energy of the water will also decrease, because H decrease, mgh is equal to U, H decrease, U also decrease. So when the water flows down, the water will loses gravitational potential energy. Well, you can see the gravitational potential energy decreases as the water moves from higher ground to lower ground. Okay, so you can see that there's a loss of energy, right? When the water flows down, there's a loss of potential energy. So where does the potential energy goes? Well, you see that there's a water wheel over here, right? So it will touch the water wheel and it will cause the water wheel to spin. So that means by the energy that was lost, it's actually not really lost. It's actually being transferred to this water wheel here to spin the water wheel. Okay, the loss of gravitational potential energy is transferred to the water wheel to rotate the water wheel, thus useful work is done. Okay, I suddenly talk about this scenario because this is very much related uh, to a capacitor situation. Okay, let's say if I install a battery over here, battery will causes, that's why I say battery acts as a pump, right? So it will pump charges. In this case, I'm drawing positive charges flowing from negative to positive terminal, same like what I sketched here. Positive charge moving from negative to positive terminal. Positive charge moving from negative to positive terminal. Okay, so I can see there's positive charge moving from negative to positive terminal. So you flow this direction from negative to positive terminal inside the battery. Inside the battery, it flows from negative to positive. So out it will flow from positive to negative. Okay, so this is the direction that it is flowing. So as it passes through the battery, as it passes through a light bulb, it will cause a light bulb to light up. Why? Because this is similar to this situation here where you go have water flow from higher ground to lower ground. So you have high electric potential, low electric potential, you flow in this direction. So you lose electric potential energy. So where does the electric potential energy goes to? The electric potential energy that was lost actually got transferred to the light bulb, causing the light bulb to light up. Okay, the electric charges loses electric potential energy as it moves from the positive terminal to the negative terminal. That loss of electric potential energy from high to low, right? The loss of electric potential energy is actually transferred. The energy loss is actually transferred to the light bulb to light it up. Thus, useful work is done. Okay, why do I do this side-by-side comparison? Because it allows me to show that actually charges are just like water. Water at higher place has greater gravitational potential energy. Charges at high electric potential terminal, the positive terminal, has high electric potential energy. Okay, if it flows downwards, it will get low gravitational potential energy. Same idea here. If it move to the negative terminal or the low electric potential terminal, it will have low electric potential energy. So if our positive charge move from high electric potential energy place to become low electric potential energy, that means by the electric potential energy is lost. So where is the energy lost to? Actually, the energy is being transferred to the light bulb to cause the light bulb to light up. So that's why I show this side-by-side comparison to let you see how does a circuit work. So if you know how does a circuit work, I'll skip this thing, later I'll come back at the end of the video. Okay, so if you know how does this thing work, now let's try to think about it. How do we bring this water, which naturally flows to the lower ground, how do we bring it up to the higher ground? Okay, that's where the electric water pump comes in, right? you need a water pump to bring the water from lower place to higher place. So this pump here is analogous to a battery. Okay, if you use a water pump that applies some electrical energy to pump the water from lower ground to higher ground, this water pump here actually is analogous to the battery, because the battery also allows us to move the charges from low electric potential place, which is the low energy place, to high electric potential place, which is the high electric potential energy place. Okay, so you gain energy through the process of passing through the battery. Water, when it passes through the pump, you gain gravitational potential energy because it goes to a higher place. Charges, when it passes through the battery, you gain electric potential energy because it goes from the low electric potential place to a high electric potential place. So the battery will pump charges in this direction, therefore you gain energy from the battery, and the energy will be lost to the light bulb to light up the light bulb. Okay, so if you read the text over here, it says the direction of motion is not natural. We know that water usually flows downward. No, water, if you let it flow, you flow downward. So flowing upward, it's a not natural kind of motion. Okay, you're bringing somewhere from lower to a higher place, you need some kind of effort to bring it. So that effort is supplied by the water pump. Similar in this case, the effort is supplied by the battery. The battery provides an external energy to bring the charges from being low energy to become high energy by passing through the battery. Okay, so you need some kind of energy from outside, so the battery supply the chemical energy to make this thing happen. So chemical energy of the battery is used to move the charge from region of low electric potential to high electric potential. It goes from low to high. So this is how you can think of how a circuit works when you apply a battery. The battery provides the energy, and the energy is lost to the load that is installed outside. Okay, so right now if you go back to our main topic, which is a capacitor, how you should think about a capacitor is you should think about a capacitor like a tangki in Malay, or a water tank in English. Okay, so if you have a water tank, what happens is you can pump water into the water tank to be stored. Okay, you can close this pipe over here and you can just pump water into the tank without letting it flowing out. So the process of pumping water into the tank without letting it flowing out is analogous to us charging a capacitor. Why is it so? Battery acts like a water pump, right? So if you put a battery, connect it to a capacitor, you are actually connecting the water pump to the water tank. So if you're connecting the water pump to the water tank, water will flow from lower ground to higher ground. Similar case over here, if you apply a battery to this capacitor, charges will move from low electric potential region, which is a negative plate, move to the high electric potential region, which is the positive terminal. So now this charge will pass through the battery, going from low potential region to high potential region. As a result, the charge here will gain an energy, just like how the water gain energy as it moves upwards. This one, the charge will gain energy as it moves to the high potential region and it comes out here. Okay, so if you want to discharge the energy that you have over here, there's a lot of energy stored in the tank here. If you want to discharge it, you will open up this pipe over here. You open the tap over here, then let water flows out. So when water flows out, the water will flow from higher region to a lower region. So the high region to lower region will cause the water to lose gravitational potential energy, right? The gravitational potential energy lost is actually transferred to rotate the water wheel. So bringing the same idea over here, if you connect it to a load, it's as if you're opening the tap and connect it to a water wheel. Okay, so if you connect it now to a water wheel, right now the charge will go from the high potential region to the low potential region, just like water flowing from upper region to a lower region. So as it flows, it will go from high to low, so that means there's a loss of electric potential energy. So where does the electric potential energy go to? Well, the electric potential energy actually gets converted into useful electrical energy, causing this light bulb to light up. So the charge initially has a lot of energy, but it goes down to low potential energy region, right? So the loss of the electric potential energy is being transferred to the light bulb, causing the light bulb to light up. So this diagram here consists of the idea of how do we charge a capacitor by pumping water into the water tank, and discharging a capacitor by letting the water flowing out of the water tank. Okay, so this is how you can sort of imagine the process of charging a capacitor and discharging a capacitor. Okay, so you can also cross-check it with this particular diagram over here to make sure you have a solid idea of what's happening. Sorry, let's give it some time. So the process of connecting to a battery is like connecting a water tank to a water pump. So you are bringing water from lower places to higher places, from low electric potential region to high electric potential region. So now if it's fully charged, that means by the water has been the tank is full, okay? The tank is full, there's no more water you can push it in anymore. Okay, if you're discharging, you're connecting this capacitor now to a load, as if you're connecting the water tank to a water wheel right now. So water will be flowing out from the higher region to a lower region. In this situation, the charge will be flowing from the high electric potential region to a low electric potential region. So as it passes through the light bulb, the energy lost, the potential energy lost by the charge will be transferred to the light bulb, causing the light bulb to light up. And at the end, there's no more water left in the tank, so we can say it become uncharged right now. Okay, so I hope you sort of understand how does a capacitor work. But before we end the session, just a light thing to talk about. I think most of you are aware from your secondary school, you learn that it is the electron that is moving in the circuit. Okay, we usually learn that electron is moving in the circuit. But right now, your lecturer here is telling you that it is the positive charge that is moving. I keep on talking about positive charge moving, positive charge moving, positive charge moving, positive charge moving. So why is it that way? Why do I insist of talking positive charge even though I know it's the electron that moves? I am aware that it's the electron that is moving, but I choose to not talk about it using electron. Instead, I talk about it in terms of positive charge. I'm not saying I'm talking about in terms of proton. The proton never move. I'm talking about an imaginary kind of positive charge that is flowing in the opposite direction to the electron. The electron is supposed to move this direction, but I don't want to talk about it in using electron. I want to talk about it in an imaginary positive charge. Why is it so? You have to refer to this note over here. Okay, when I say electric charge that is moving here, I'm always referring to the positive charge over here. So, but that doesn't mean by the proton is moving in the circuit. It's definitely not the proton that is moving. The proton is fixed in the nucleus cannot move. What moves is actually the electron. In fact, in reality, it's the electrons that are moving in the reverse direction. So when you connect a battery like this, what happens is not actually positive charge moving downward, from positive terminal to negative terminal. What actually happened is the electron flowing from the negative terminal to the positive terminal. But why do I not talk about the real thing that happened? Is because of this. However, we are more used to saying things gain potential energy when it moves from low to high. When you pick up something from the ground, move it to a higher place, it gains potential energy. That is what we humans are used to. We let the thing fall from a higher place to a lower place, it will lose gravitational potential energy. That is what we are used to. Okay, but if we talk about it in terms of electron, if you insist on talking about in terms of electron, we know that the electrons over here, if you look at the battery, the electron will move from high to low. You move through the battery from high to low. So based on our perception, based on our logical thinking, our everyday life thinking, this is as if the electron is falling. So our idea, our head usually think if something is falling, it will lose electric potential energy. But that's not the case. We say that a battery you only provide energy to let it gain electric potential energy. So in reality, when the electron goes from the high potential region to the low potential region, it is actually gaining energy, which is a bit counter our logical thinking. It's not really intuitive, it's counterintuitive to know that electron, when it go falling from high to low, is actually gaining energy. So it's a bit counter our it's a bit counter our usual logical thinking. Is counterintuitive. That's why it's not very uh it's not very friendly to talk about things in terms of electron, because it's not behaving the way that we usually think how things behave. So because of that, we will stick to electric charges, which is some kind of charges that is the reverse of electron. It's a it's an imaginary thing. It's a reverse of electron, and because it's a reverse of electron, it will move in the reverse direction of the electron. So reverse direction of electron means by it will go from low to high in the battery. It will go from low to high. So low to high, we know is as if a thing is moving upwards, right? So if a thing moves upwards, it gains electric potential energy. So right now, the positive charge, this imaginary positive charge, will gain energy as it moves through a battery, just like how we previously say things. How we usually imagine things. Going from low to high, you gain energy. So you can see that positive charge here actually makes more sense to explain. If you want to explain in negative electrons over here, it is still correct. It's actual thing that happened, but it's so difficult to understand because it is not the way it's not the way things behave in everyday life. So we switch it to an imaginary things that is moving in the opposite direction of the electron, so that we can see that as things pass through the battery from low to high, it gains energy. Okay, so that's the reason why you see me talking in terms of positive electric charge. Okay, instead of talking it in terms of electron, I'm always using positive electric charge, and I'm going to stick to positive electric charge in the future. I'm not going to talk about electron anymore because electron is just so counterintuitive to understand. Okay, so that's it for this video. I'm going to focus on just how a capacitor works, and in the next video I'm going to define things like capacitance. I'm going to talk about how do you affect capacitance, things like that. Thank you very much.